Okay, well, hopefully all of the technology is working and you can hear me and you can see my slides. Um, I'd like to start just by thanking Aunion Tech for organising this webinar and inviting me to speak. I'm very happy to be able to present a little bit about Covesion and how we are developing waveguides for quantum applications and present some of the work that we've been doing with particular quantum projects and quantum technology types. So I'll start just with a little bit of background, just to talk about the motivation for the work here. The map here just provides an overview of the amount of investment across the whole world in quantum technologies. And it's estimated that currently the world total in quantum investment is something close to $40 billion. So there is an enormous amount of money being invested in new quantum technologies. And that investment here is only the investment that is coming from public entities. So that would be government investment into universities and research labs. So that number doesn't even include the amount of private investment that is going in from venture capital, direct company investment and such like. And obviously there's very large investment in North America and in Europe, but also in China. Obviously, there's a huge amount of interest in China in these new quantum technologies. And the quantum technologies that we're talking about here cover everything from quantum computing, quantum sensing, quantum timing, quantum cryptography. And one of the key things that this investment is funding is to move these technologies out from the research lab and into manufacture and into technology systems that can then be applied to real world problems and can be put into real world situations, so that can actually be used and operated in the real world. So what I'll cover in my talk is a little bit about how we're moving what we've done in terms of research into real products, real applications, and what our end users are doing with those. So just a little bit of background about the company. So Covesion as a company, we're experts in wavelength conversion of lasers. Our underpinning technology is PPLN, or periodically poled lithium niobate. We've been trading since 2003, so we've been in business for more than 20 years. The origin of the company is a spin out from the Optoelectronics Research Centre at the University of Southampton. And on the map on the bottom right there, you can just see where our location is. So we're situated on the south coast of England, about an hour and a half to 2 hours away from London, southwest of London. We're a very rapidly growing company. We're up to a company of more than 25 people now. So the picture on the top right there, which is the team outside our company office, is somewhat out of date now. We need a new picture showing how much the team has grown. And as a company, we are very proud of the fact that we do everything ourselves. So other than buying in the raw material, so we buy in lithium niobate in wafer form, but everything we do from that point onwards, we do ourselves. So we do in-house the fundamental design and modeling of the PPLN device, and then all of the manufacturing processes we do ourselves. So we do the polling, the dicing, the polishing, all of that ourselves. We have our own company facilities in our own building, which are a mix of clean room facilities and test laboratories. And then we also use laboratories at the University of Southampton. So we use their clean room and some of their larger equipment. So things like metal deposition, indiffusion, and the dicing, which I'll talk about a little bit later in terms of waveguide manufacture. So that's done at the university. But then, so all of the fabrication steps we do ourselves, and then all of the quality control, the testing, the packaging we do. So we're very proud that we do everything ourselves and have complete control over all of those processes. So why are we interested in periodically poled lithium niobate? Well, the reason is that lithium niobate itself is a non-linear optical material with a very high second-order non-linear coefficient. And it's also a material that can be periodically poled. That means that you can nanofabricate a grating structure into the material that allows you to quasi-phase match. And I'll talk about that a little bit later. The outcome of that is that it's a very flexible material that can be tuned for particular wavelengths. The transmission range of the material runs from 400 nanometers in the blue or UV right out to the mid-infrared around 5 microns. And by tuning the grating that you fabricate into the material, you can access that full transmission window of the material. So you can manufacture devices that perform second harmonic generation to short visible wavelengths, and you can manufacture devices that perform up conversion and down conversion right into the mid-IR. So an extremely flexible material. The key part of the technology is the periodic poling. So this is where we fabricate a periodically inverting domain structure into the material. What that does is it allows you to access the highest nonlinear optical coefficient in the material and perform quasi-phase matching. So on the right-hand side of the slide there, the little photograph inset shows you one of our crystal chips. And then the larger picture shows you a microscope image where we've zoomed in to show you the grating structure, and then a further zoom in so you can see some of the details of the quality of the grating that has been formed. So in this example, we have a grating that is about 6 microns in period. And you can see from that zoomed in picture that we've got very high quality domain formation. We have very uniform domains. We have no missing periods. We have a well-controlled period, and crucially, we have a well-controlled duty cycle. So the duty cycle is very close to being 50-50, and that's important to ensure high conversion efficiency. The way we form the grating in the material is to apply a high electric field across the material. And it's that high electric field which forces the crystal domain to orient with and against the electric field. And that's done on a wafer scale process. So we pattern a whole 3-inch wafer with the grating structure using standard lithographic techniques. And then we have a proprietary method of applying a high voltage, tens of thousands of volts across the material to periodically invert the domains. So what you end up with is a crystal material with these inverted domains. If you shine your input light into the crystal with the appropriate orientation, perpendicular to that inverted structure, you can obtain quasi-phase matching. So by matching the grating period with the input and output light that you wish to generate, you maintain the phase match of the overlapping fields through the whole crystal length. The plot on the right shows you how something like second harmonic generation evolves along the propagation direction of light through the crystal, so that you can see as you move through the crystal, the second harmonic intensity builds up periodically as you move through the periodic structure. So that's the red curve there. Whereas the black curve shows you the situation if there was no quasi-phase matching. So you get no buildup of nonlinear optical output. So as I mentioned before, what you have in PPLN, and other materials can be periodically polled as well, I should mention. So things like KTP can also be periodically polled. But these materials that can be periodically polled allow you to tailor the output wavelength by the material and by the period. So that's a little bit of background to the technology itself. What I'll move on to now is some examples of specific quantum applications where we're applying this. So the first example is a project that we worked on called CASPER, which stands for Cold Atom Space Payload. So this is a quantum sensing application here. And the project outcome was to produce a gravimetric sensor that could be loaded into a small satellite, so a CubeSat, which would then perform gravimetric monitoring from space orbit. And the ultimate use here is to do environmental monitoring. So by performing high sensitivity gravity measurements, you can map things like polar ice maps to look at the effect of global warming. You can also look at underground water tables when you're doing urban planning. So there are some very important applications for high sensitivity gravity sensing. The project challenges here are that we want to make the satellites as small and low cost as possible. We have a limited power budget and we have a limited size and weight. Obviously, all the components used within the satellite must also be space qualified and therefore robust to radiation, vibration, temperature, etc. And of course, since the satellite will be in orbit for a number of years, we need long-term maintenance-free operation. So in this case, the technology chosen for the sensor itself was based on a rubidium magneto-optical trap. And you can perform the gravimetric sensing part of it by performing atom interferometry. Now, a rubidium MOT, magneto-optical trap, requires a high precision laser light source operating at 780 nanometers to perform the cooling, the repumping, and the interferometry functions. So the solution chosen here was to make use of space-qualified seed lasers operating at 1560 nanometers, and then perform second harmonic generation on that seed laser to generate output light at 780 nanometers, thereby providing a robust source for the rubidium MOT itself. For this application, we were looking at generating around about 40 milliwatts of output power based on pumping at 300 milliwatts. So the next slide shows you the outcome of the project. So what you've got here is the CubeSat itself with the covers off, showing you the internal systems that have been put together. At the top, you've got the flight control computer, which does the attitude control, etc. In the middle, the silver section there is the optical system. So in the case of Covesion, what we developed here was a periodically polled lithium niobate solution that would perform the second harmonic generation and was suitable for integration into the optical system that was delivering the 780 nanometer light. And then at the bottom in the middle there, you've got the experimental chamber itself. So that contains the rubidium atoms held within the trap via the light and the magnetic field. Unfortunately, follow-on funding wasn't available to actually fly this satellite. However, it did go through pre-flight testing and was shown to be robust to vibration, temperature, and radiation. A second project was a project called Pioneer Gravity. And again, this is for a gravity sensor based on a rubidium magneto-optical trap. However, in this case, the gravity sensor is to be land-based rather than space-based. And the end application here is for site surveying. So it's estimated within London alone, more than £1 billion UK per year of disruption is caused when holes are effectively dug in London streets and underground services are discovered that weren't expected. And this is because London is such a complex city, many of the underground services have not been accurately mapped. So if you can accurately map below ground, looking for voids, services, pipework, electrical cables, it can be enormously beneficial before you start adding any infrastructure or doing any tunneling work. The challenges with the project here were to develop a technology that is more sensitive than the incumbent technology. The incumbent technology is a classical mass and spring sensor. The mass and spring sensor system is very expensive, a few £100,000 per system. It's also not robust. So if it's tilted by more than 15 degrees, it goes out of calibration and has to be returned to the factory for recalibration. And the sensor also needs to be portable for use in the field, so transportable by truck. In this situation, because the application requires higher sensitivity, we were looking to generate about a watt of light at 780 nanometers to drive the optical trap. And again, a very successful project with the picture here showing you the resulting gravimetric sensor system. So the system is portable. On the right-hand side, you have the vacuum chamber, the rubidium dispenser, the magnetical coils, all holding the atom chamber system. On the left-hand side of the picture there, you've got the control systems, the control electronics, the laser source, and it's all delivered through the flexible cable. This project has been so successful that one of the partners, the University of Birmingham, has now set up a spin-out company specifically to further develop this technology and commercialize it. So the key thing from these projects is that what they do is they provide us with target specifications for the optical element to be used to provide the laser light. So for these projects, what we were looking at doing was performing second harmonic generation on robust telecoms lasers to generate 780 nanometer light through rubidium atom trap cooling. The nonlinear optical device needs to be rugged. It needs to be of use in harsh environments, be that space or aerospace or land-based vehicles. The device itself needs to be able to be packaged. So the key thing here is that we want to move the technology out of the lab and into real use situations. If we have a robust device that can be packaged with fiber coupling, then that becomes more beneficial to the end user. So we need high launch efficiency. We need good coupling efficiency between fiber and the waveguide. We need high conversion efficiency, obviously, because we want to minimize the amount of pump laser light that we're using. And the projects here I've mentioned require watt level output in the second harmonic. So the technological route we've chosen is to develop a waveguide structure. In our case, the waveguide structure itself is a diced ridge waveguide based on zinc indiffusion into the lithium niobate wafer. Covesion is a commercial company. We want to commercialize this technology, and we want to be able to support quantum applications as they grow in use and volume. Therefore, we need a manufacturing method that allows us to make hundreds, thousands of these devices every month. That being the case, we've developed a very simple manufacturing process that's based on 4 steps. Step 1 is to take our lithium niobate wafer and pattern the periodically poled grating into it. Step 2 is to deposit a layer of zinc, and then step 3 is to indiffuse that zinc layer. That zinc indiffused layer at the surface of the wafer gives a planar waveguide structure. So by indiffusing the zinc, you get a refractive index change through the top of the wafer, which gives you the confinement within the surface. We then take that zinc indiffused wafer and dice our ridge waveguides into the wafer. So you can see the resulting outcome in diagram 4 there, where you have the patterned wafer and we've now diced a ridge structure into the surface. Everything so far has been done at wafer level. So we process on 3-inch wafers. So we have good scalability, good reproducibility by doing everything at wafer scale. And once the ridges have been diced into the wafer, we can then dice out the final waveguide chips for packaging. Key part of our process is the dicing itself. So hopefully you will see a video playing now. And this is a video of our dicing process. So for the dicing process, we make use of a very high precision dicing saw, which is housed within the University of Southampton. The dicing process is a ductile process. That means that when we cut the surface of the wafer, we don't have any chipping, cracking, damage of the surface. And that's extremely important because that gives us a very high quality waveguide with minimal processing. As you can see, the process is still being done on the full wafer at this stage. As I mentioned, the dice or the sawing process is a very high quality process which gives a very smooth finish. So on the left-hand side here, you can see an SEM image of 2 of our ridge waveguides. You can see that the sidewalls are very smooth and the end facets are very smooth. On the right-hand side, you've got a white light interferometric image from which we can measure the surface roughness. And we've got a surface roughness measured less than 0.3 of a nanometer. That's equivalent to a typical lapping and polishing surface. So we have very smooth sidewalls and we have very smooth end facets. What this means is that we don't have to do any post-processing on our waveguide. We don't have to do any etching or polishing. So again, this means that we have a manufacturing process that minimizes the number of steps and minimizes the amount of handling by any operator. And crucially, is all done at the wafer scale. So that's how we manufacture our waveguides. What I'll talk about now is how we test them. So the schematic here shows how we test our waveguides. We have a tunable telecoms laser, which we amplify, and then we put through a zoom collimator to focus the pump light onto the entrance aperture of the PPLN waveguide. The waveguide needs to be held at the correct temperature to allow the phase match. So we hold the waveguide in an oven. The output light is then collected and sent to the detector. We can measure the pump light before and after the waveguide, and we can measure the pump light on and off phase match, and we can measure the second harmonically generated output light after the waveguide as well. By measuring all of those parameters, we can measure coupling efficiency, propagation loss, throughput, and conversion efficiency of the waveguide. So we can fully characterize the waveguide. The photograph on the right shows a waveguide under test in our test laboratory here at Covesion. And then the images on the left-hand side show you the mode output for the pump light at 1560 nanometers and the second harmonic light at 780 nanometers. So what I'm showing here is that our pump light okay. Sorry. Apologies for that. That was our fire alarm being tested in the that was our fire alarm being tested in the building. Right, hopefully that didn't disturb you too much, and I'll carry on. So as I was saying, images on the left-hand side here show the mode field output at 1560 and 780 nanometers. For the 1560 nanometer light, you can see that we've got a mode field diameter of around about 10 microns. And this has been intentionally designed into the waveguide. By having a 10 micron mode field diameter, we can achieve very good coupling to PM1550 fiber. And this is important for packaging the waveguide into a module that is easy to use by the end customer. We typically achieve 80 to 90% coupling efficiency on the input of our fiber coupled waveguide modules. You can then see that the 780 nanometer light has a slightly elliptical shape. That's because the waveguide itself, it is designed for single mode operation at 1560. So you get some elongation of the 780 nanometer light. This means that you do get some additional coupling loss on the output when coupling into a fiber. However, there are things that you can do to improve that, such as using lens coupling into an output fiber or using things like tapered pigtails. So here are some characterization results showing the performance of our waveguide chips themselves. The horizontal axis there shows you the pump power that we're applying to the device, and then the vertical axis on the left shows you the second harmonic output power, and on the right shows you the conversion efficiency. In this case, we're generating more than a watt of output power for a little bit more than 1.6 watts of 1560 nanometer pump light. And we're achieving a chip efficiency of about 70%. I should highlight that this is a free space chip. So this is where we're free space coupling into and out of the chip. This is not a packaged result. We can measure the launch efficiency to be about 80%. And then if you look at the spectral properties of our light, what you're looking to achieve here is a high quality sync function. And the quality of the sync function is a measure of the uniformity of the device. The inset shows you low power pumping, and the larger image is high power pumping. And you can see that there's no change in the sync profile as we move from low power to high power, showing that we've got very good uniformity of our waveguide. Going to higher pump powers, we can achieve up to 2.5 watts of output for about 3.4 watts of pump power. Again, this is not a packaged device, so we're looking at free space performance in this case. Key thing here is that we've demonstrated that we have a waveguide design and structure that is robust and can deliver the high output powers needed for rubidium optical trapping. Everything I've talked about there is dealing with the generation of 780 nanometer light for rubidium trapping. Obviously, there are other wavelengths that are of interest. There are many applications for other ions and atoms, both in quantum sensing and quantum timing. Currently, we're working on generating short wavelength light for calcium ions as a frequency standard, and people are also interested in generating 422 nanometer light for strontium. What you have here is the first results of our waveguide designed to produce light at around about 400 nanometers. In this case, we're having to go to narrower ridge width to ensure single mode operation. So we have a 7 micron ridge width, and we also have a much shorter polling period because the wavelength we are generating is much shorter. These early results show that we've achieved a few milliwatts of output power for a few hundred milliwatts of pump. So this is a really encouraging result that shows that the underpinning waveguide technology we have can be pushed to shorter wavelengths. So we can go to shorter wavelengths. Can we go to longer wavelengths? And the answer is yes. So in this project, which was called Mid-IR Upconversion Single Photon Detection, or MIRAS, what we were doing here was using a PPLN waveguide to upconvert mid-infrared light to the visible region. The application here was to perform mid-IR sensing, but to use a silicon single photon avalanche diode to do the detection. So the silicon SPAD has very high sensitivity and can be gated for time of flight measurement. SPADs are not yet available for the mid-IR operating range. So the solution is to perform wavelength conversion from the mid-IR to the near-IR where a SPAD will operate. Images on the bottom right, so the grayscale image shows you an upconverted image where we had test objects in the lab illuminated by a mid-IR source, and then the output of the SPAD showing you the generated image. And then the color image next door to that is actually time of flight information. So by pulsing the illuminating light and gating the detection, we can perform time of flight measurements and get range information. And this is of interest for people doing drone observations, mid-infrared gas sensing, and other such applications. So what we've shown there is that we can go both to short wavelength and to longer wavelength, and we have viable waveguide technology. One of the most important things for quantum technology and quantum applications is that the industry builds a robust supply chain that takes the technology out of the lab and into the real world environment. We've been very focused on that. So what I have here is examples of how we've taken our waveguides and then packaged them into modules which allow the end user much greater ease of operation. So what we have here is a variety of examples of fiber-coupled modules where we have fiber in the input, fiber on the output. We also have free space output. These modules can be combined with temperature controllers so that we can offer a complete solution for system integration. So where we work with OEMs, we can provide a complete solution. I will skip this slide and just give you an example of the performance of our waveguides within a full package. So the left-hand side shows you our compact package with fiber coupling on the input and the output. And then to the right of that, you have the output power curve showing that for 2 watts of pump power, we're generating 1 watt of output. This was a result from another one of our R&D projects, so it was a project result. And at the bottom, you've then got lifetime test data, where we've run one of our modules out to 1,000 hours of operation and shown stable output over that lifetime with 1 watt output. In fact, all of the drift and noise we're seeing on the second harmonic output, we can attribute to the pump source itself and the amplifier that we're using. So I'll just finish with a quick summary. What I hope I've shown you there is how quantum applications and quantum technology are driving the solutions that we're developing at Covesion, and how they've driven our waveguide development and how they've driven our packaged waveguide development. Our focus the whole time is with providing end customers with easy to use solutions so that they can implement these in larger systems. Our periodically poled lithium niobate waveguide is a key part of this technology because it provides a robust, high efficiency conversion solution. And I would like to highlight that we're at the forefront of developing this technology. And with that, I'll finish and thank you very much for your attention.